Enjoy calculations. Calculations are going to be fun. We want to quickly go through the calculation questions in this paper again. So what we're just going to do is see how we are going to remember the formulas. Okay, one more round. And I want you to practice this about 10 times, whatever. So let's do it. So this is how we're going to do it. We start with week one, okay? We start with week one, which is of course static electricity, right? And let's quickly go through the formulas and let's see. So in here you only have to know three formulas. So let's see what I mean by that. Okay, there are only three stages or three different types. The first one is going to be Coulomb's law, which is for electric force, and we know that it is going to be, you can first put the Coulomb's constant and then say Q1 Q2 over R12 squared. And these ones are magnitudes. That's why I left some space. So this is what you're going to do. This is going to be Coulomb's law. We have Coulomb's law first of all. And then that's going to be formula number one, right? So maybe I should put the box outside and then call this formula number one. Then formula number two is going to be for E, okay? And there are two of them, and we all call them the number two. That is for E. The second formulas we'll do are for E, which is E is the electric field strength. It is the force per unit charge. And then the other one is to say that the electric field strength, if you want to find it, you can calculate it by saying KE multiplying Q over R squared, okay? KE, remember, is Coulomb's constant, and it is there right here, okay? 8.99 times 10 to the power of 9. Then now, the third, we've done this one, and we've done for E. The third and final one will be for flux, okay? The third and final ones are for flux, which one says flux is equal to EA cos theta, okay? And the other one is Gauss law. It's still for flux, which says flux is equal to Q surface or Q in divided by mu zero, okay? This is the Q, the total charge inside the surface, divided by the permeativity. And this is going to be it, and you'll be done with the first part. So here are the formulas which you are going to need, okay? How is that? Great, right? So this is going to be the first part. We have only three parts, okay? Now let's go to the second bunch of formulas, which is now we will talk about weeks. Okay, this is week 1 and 2. Then we can have weeks 3 and 4. Okay, but we first do part 1. Weeks 3 and 4, part 1. And this is going to be electrostatic work, okay? Electrostatic work. So here we have seen that there are only three formulas. You can remember them. Come on, I know you can. Okay? Don't remember them as more than that. Just remember them as three. One for F, two for E, and two for flux. Okay? And remember that this theta is between, it is the angle between E, which is the field lines, and the normal to area. Okay? And normal to area, A to A, which is the area. Okay? Now we go to electrostatic work, okay? We want to put the formulas for electrostatic work, which again, we only have 4 of them. Let's put them. First one is going to be for work itself, and it can be put in 2 versions, which of course you only need one really. This one is to say force times displacement is work, okay? Then this changes to be work is equal to, because from here, we can change and find that if we take Q to the other side, we have QE being equal to force. So force is QE. This is what we are going to use on the other side, okay? So here we're going to say work is, instead of, we say it will be QE delta X, okay? It's QE delta X, okay? Which we'll write to say it is QE multiplying XF minus XI. That is the delta X. So this is the second one. It's just the formula for work. You can write it as QE XF minus XI, right? So the first are for work. Then the second is for change in energy, which is just equal to negative of work done, okay? Change in potential energy. This is the change in potential energy. It is just equal to the work done, okay? So we have seen 2 for work. We can just say that. then one for potential energy, the change in potential energy. Then we'll have the other one for potential now, which is just going to be Ke Q over R. We saw the other one was Ke Q over R squared. That was E. In here we have Ke Q over R. Then we're going to have V being equal to the other one, the V for potential. It is the potential energy per unit charge, okay? Potential energy per unit charge. That is for the definition of V. All right, now once you're done with this, so remember we said there are 4. So this is 1, this is 2 for delta U, 3 is for V, then the 4th one is delta V, okay? These are the 4th one. So what will be delta V? It will be just delta U over Q from here, okay? Then from here, we know that delta U is negative of work. So delta V will be equal to negative work over Q, okay, which is the other version. Then the last and final version of this 4th formula is going to be delta V is just going to be equal to negative of E delta X. Put this, you may need it. Negative of E delta X, okay? It just came from dividing work by Q, okay? Because work is QE delta X, but Q is now gone, so it'll be just E delta X. But remember that delta V is negative of work, so that's why it is negative. That's the 4th formula, and this 3rd, this is the 2nd, this is the 1st, okay? So now remember, what is it? 1 for work, 1 for delta U, 2 for V, 3 for delta V, and you're done, okay? For delta U, remember, it also means if delta U is negative work, it also means work is equal to negative of delta U. That's the relationship they have, okay? All right, now we go to the last part, which is going to be capacitance. So we can say weeks 3 and 4, part 2, okay, which is the last thing you're going to need to know for your test, capacitance. These are the formulas we need. Okay, so for capacitance, right? How many formulas do I have again? 4, okay? So we saw here we had 3, 1 for F, 2 for E, 2 for flux, okay? Then here we had 4, 1 for W, 1 for delta U, okay, 2 for W, we can say 2 for delta U, but 1 for delta U rather, then 2 for V, then 3 for delta V, okay? W, delta U, V, delta V. How easy is that? Now we are here and we have 4. What are the 4 formulas? What are the 4 formulas? Okay, what are the 4? 1 is for, we can say that 1 is for E, okay? In the first part, oh my goodness, let me make sure that this is really closed behind. Then I'm going to use a different color, which I haven't used before. Right, we start with E. Okay, in capacitance, we have E being defined again. E in capacitance is different, okay, from this E which you had here. Okay, it's very different. So what is E in capacitance? You start by saying sigma over mu 0. This is E, and then you have the other E, which is E is equal to delta V over D. So what is this? This sigma is going to be charge density. This sigma is charge density. Over, we know that mu 0 is the permittivity of free space. Delta V, this is going to be the voltage between, the potential difference between your 2 plates. Then D is the separation. This is now when you have your 2 plates. So you can have 2 plates and you want to find E. So make sure, just write them down, and you're going to use one of them to find E in capacitance. Then once you have it, this is the formula number 1. Then formula number 2 is for this sigma, charge density. It is what? Charge over area. Okay, it's charge per unit area. This gives you the charge density. Then we go to formulas number 3. The third formulas now, the third bunch. So here, what was the first one about? E. It was E. And how many do we have? 2. Sigma over mu 0 and delta V over D. Then we have sigma. Then now we can go to capacitance. Capacitance just as, it's nothing. Capacitance has 3 versions. So you just say capacitance is equal to, we know that it's charge over voltage. So put that one. This is for the definition of capacitance, the charge stored and the voltage divided, the voltage between the 2 plates, whatever. So this is going to be now capacitance. Then we go to the second. Capacitance will be mu 0 A over D. That is if there is no dielectric. Then the last one is capacitance is equal to mu 0 K okay? Or you can say K mu 0. This is just mu 0 if there is no dielectric. If the dielectric is there, it's K mu 0, then A over D. K. A is the area of one of the plates. D is the distance between the two plates. This is the third one. Then the fourth one, so in capacitance, you see how easy it is. 1 for E, 1 for sigma, 3 for C. Then the last one is just going to be for energy stored in the capacitor. And you'd be done. Come on. Energy stored in the capacitor. Here we say energy. It has three versions, okay? It is either equal to half. Everything is half. Half, half, half. Or we can say it is also equal to half, or we can say it is also equal to half. Okay, when we put, remember for capacitance, we have three things, C, Q, and delta V. When we put anything which is not Q and C, they'll be multiplying. So it's half. What does it have? It is Q delta V. Or half CV, C delta V squared, okay? C times delta V all squared. Or it is half of Q squared over C, okay? These are the three versions, and you are done, okay? So let's put it again. I don't know if I have space. Oh my. So I can say energy. This is for capacitance. Energy stored in a capacitor. It will be half of Q delta V, or half of C delta V squared, or half of Q squared over C. And you are done. This is everything you're going to need to know, and it's just that you should also know about capacitors when you combine them in series and in parallel. But once you know this, you have everything and you can do the calculations. So with this, we are going to start doing the calculations. Let's go through the calculations in this paper. We see any calculation that we're going to need. Practice, okay? Go through this again and again. Practice how to list your formulas, then you're going to be fine, all right?